Hello, good morning everybody. In the last class we have seen up to methods of surface drainage. What are the various methods? One, by longitudinal side drains. Second, catch bins and inlets in urban areas, providing damp proof cores either using a bituminous blanket or geosynthetic material or cement concrete layer in the form of a bed, providing proper camber, providing sufficient slope to the sides, and keeping the level of carriageway at least 60 centimeter above the HFL. Carriageway at least 60 centimeter above the HFL. Suppose if this is the HFL, the pavement should be constructed by keeping at least 60 centimeter above the HFL. Now, side drains for road in embankment. The figure shows clearly the section of such arrangement. It is necessary to provide side drain on one side or both sides, depending upon the necessity and quantum of water to be drained or taken into the side drains. When road is constructed in embankment, side drains should be at least 2 meters away from bottom edge of an embankment. These considerations should be clearly followed. Depth of side drains is kept 1 to 1.5 meter to prevent the entry of drain water into the embankment. So whatever the water is drained, that should not come onto the embankment. That's why the depth of side drains itself is kept at 1 to 1.5 meter, means around 3.3 feet to 3.3 plus 1.7, around 5 feet. 3.3 to 5 feet below. So shoulder, this is side drain here, side drain. This is the road, this is the shoulder, this is berm, this is camber, this is berm, this is side drain, this is road or pavement or carriageway, this is camber provided, and this is the shoulder. So water will come here and then it will lead to side drain. This side drain should be kept 1 to 1.5 meter to prevent the entry of drain water into the embankment. Side drains for road in cutting. The previous sketch was about embankment. Now this is in cutting. When the road comes in cutting, this is the carriageway. This is the carriageway. This is the carriageway. This is formation width including the shoulders and separator if any, that we have defined. These two are the side drains. This is spoil bank. This is slope of the ground. Slope of the ground. This is the ground level. This is also ground level. In cutting we are taking the pavement. Therefore the side drain is provided on both the sides. Catch bins and inlets in urban areas. See, very nice photograph is being given so as to understand clearly catch bins. What is catch bin? It is a structure like chamber constructed on a sewer line. Over the sewer line, it is required to be constructed. Water from pavement surface is collected in catch basin and discharged to the sewer line. The catch basin, that is catch pit, is provided with grating to prevent the entry of rubbish into the drainage system. Grating just like a mesh. Even at our homes, in bathroom, kitchen, wherever the water is shown access to go into the drainage, we are providing mesh type small. We do not call it as grating there. Here it is called as grating to prevent the entry of rubbish into the drainage system. Shoulder drainage. Shoulder also should be provided with suitable drainage. This is subgrade material, granular subbase, base course, and percentage of sloping in percent. Granular material, this is unpaved shoulder, this is paved shoulder. This portion is unpaved, this portion is paved shoulder. That means this is impervious, this is pervious. Granular material is used as a filter also. For quick drainage of water from the roadway, the shoulder surface has to be properly sloped. That means the sloper is also provided 0.5% here, n plus 1% here, n plus 0.5%. Slope is provided so that the water can be drained off. A continuous drainage layer 75 to 100 mm thick can be laid under the shoulder at the bottom level of the subbase or the bottommost granular subbase layer and extended up to the edge. It can be extended up to the edge. A paved shoulder, if provided, should have a cross slope of at least 0.5% more than the camber. The unpaved shoulder beyond this should be a further 0.5% steeper as shown in figure. That's why this is 1%. 0.5 further steeper than on paved shoulder. This is 0.5, this is 0.5 plus 0.5, 1%. Very knee sloping of camber. Median drainage. Except for a median less than 5 meter wide, it is not desirable to drain the median area towards the pavement surface. 1.2 to 1.8 meter wide median provided with curbs and always paved. 1.8 to 5 meter wide median usually turfed and crowned so that surface water could run towards the pavement, maybe with or without curbs. Third point, median wider than 5 meter or without any curbs at edge. If carriageway slopes towards the median, central drain may be made to carry the runoff and slope should not be steeper than 6:1. When the median has only earthen surface, it should not be crowned because it can result in soil particles being carried to the pavement surface, making it more slippery. Subsurface drainage. Removal or diversion of excess soil water. So far we have studied little bit detail about surface drainage. Now we will see about subsurface drainage. What is the meaning or definition? Removal or diversion of excess soil water from subgrade is termed as subsurface drainage. That's all the meaning of this word, subsurface drainage. The change in moisture of subgrade are caused by the following. What are those? Fluctuations in groundwater table. Usually water table will be fluctuating depending upon light rainfall, heavy rainfall. When heavy rainfall falls on the location or area, water table suddenly increases and vice versa. Seepage flow, from anywhere it could be possible. Percolation of rainwater through impervious soil. Movement of capillary water from underground, that is from subgrade itself. In subsurface drainage, it is practiced to keep the variation of moisture in subgrade to a minimum when subsurface drainage is required. When road is in cutting and water seeping from sides. When road is near the foot or hill and is likely to be damaged by water flowing down the hill. Subsurface drainage is required. When road is passing through plain area and water is likely to be accumulated on sides, then also it is required. Where water rises up to subgrade by capillary action, where subgrade soil is affected by the drain passing near the road. These are all 5 points, or few more points also should be kept in mind why or when subsurface drainage is necessary. How to implement subsurface drainage? 1. Lowering of water table, it is possible. Controlling seepage flow, it is possible by putting a barrier. And controlling capillary water. All these three, if we follow, definitely we can implement subsurface drainage. Lowering of water table, how it is possible? In order to the subgrade and pavement are not subjected to excessive moisture, and the water table should kept at least 1 to 1.2 meter below the subgrade. 1 to 1.2 meter below the subgrade we should keep. In places where water table is high, to take the road formation on embankment of height not less than 1 to 1.2 meter is the best approach. That means a place wherein water table is high, to take the road formation on embankment of height not less than 1 to 1.2 meter is the best approach. But when the formation level is at or below the general ground level, at or below the general ground level, it is necessary to lower the water table. There is no alternative. We have to lower the water table so that the formation level of the road at or below the general ground level can be kept dry. If soil, next point, if the soil is relatively permeable, like earth, gravel, road, etc., it may be possible to lower water table by constructing longitudinal drainage trenches with a drain pipe and filter sand, and top of trenches is covered with clay seal. The depth of trench depend on the required lowering of water table, how much we can able to lower it, distance between the drainage trenches, what is the distance we are maintaining, and especially type of soil. All these three factors will influence the depth of trench. Accordingly, it is designed and finalized before we provide it. Next, lowering of groundwater table in pervious soil. Impervious soil. You see, the longitudinal trenches on either side. This is the pavement. This is the pavement. These two are the longitudinal trenches, shoulder, side drains on either side, carriageway. This is, as we have already pointed out in the previous slide, this is 1.2 meter. This is original groundwater table, GWT, water table, and longitudinal drain pipe are provided at the bottom of the trench. Therefore, this groundwater table is lowered by this much. It is lowered. If the soil is relatively pervious, longitudinal drainage trenches with the drain pipe backfilled with filter sand can be used. Filter sand. The depth of the trench depends on the extent of lowering required, soil type, and distance between the trenches, which we already studied in the previous slide. A typical arrangement is shown in this figure. Is it clear? Next. Lowering of groundwater table in impervious soil. Impervious soil. If the soil is relatively less permeable, the lowering of groundwater table may not be adequate. Hence, in addition to the longitudinal drains, transverse drains have to be installed at suitable intervals in effectively drain off the water. Not only longitudinal trenches along with the drain pipe, also cross drainage in the lateral direction or perpendicular to the longitudinal drains at suitable intervals if we provide. In case of impervious soil, the water table can be lowered very quickly. So this is section, this is in plan, top view. So the original groundwater table which was here has been reduced to the dotted line shown is the lowered groundwater table. This is the way how in case of less permeable soil we can lower the groundwater table. Simply with longitudinal drains it may not be adequate or adequately we cannot lower as in case of pervious soil. Now, control of seepage flow. Seepage flow. When the general ground as well as impervious strata below are sloping, seepage flow is likely to exist. When the general ground and as well as impervious strata below are sloping, seepage flow is likely to exist. If seepage zone is at depth less than 0.6 to 0.9 meter from the subgrade level, longitudinal pipe drain in trench filled with filter material and clay seal may be constructed to intercept the flow. The longitudinal drains with a pipe can be provided when there is a slope from both the sides. It is possible to intercept the water and it can be removed from the position. Thereby pavement and subgrade can be kept dry. Control of capillary rise. For that pervious layer, this is subgrade, highest level of groundwater table. This is the carriageway, this is shoulder. If the subgrade is clayey, the system of subsurface drains on either side will not be effective in view of very low permeability of the subgrade. Clayey material is having less permeability. Therefore, the system of subsurface drains on either side will not be effective in view of very low permeability of the subgrade. In such a case, the subgrade has to be raised with a free draining material or a capillary cutoff has to be applied as shown in figure. This is the capillary cutoff. This is the capillary cutoff. The location of the cutoff should be above the level of capillary rise expected for the clayey subgrade. So that is to be determined first. Depending upon the type of soil present in the subgrade, the location of the cutoff should be above the level of capillary rise expected for the clayey subgrade. Clay cutoff for a clayey subgrade. So even cutoff material also is of clay material only. Capillary cutoff for a clayey subgrade. Design a filter material. Hope that this can be covered in the next class. Thank you.